My name is Georgia Chalvatzaki. I am a research group leader here at TU Darmstadt, and my group is called IROSA, from Intelligent Robotics for Assistance. I am also a postdoc at the IIS group, the Intelligent Autonomous Systems of Jan Peters, and I will talk to you a bit about my recent work here in TU Darmstadt on accelerating robot skill learning using demonstrations and models. So let me start here. Okay. So intelligent robot behavior. So we envision our robots to be able to execute multiple tasks, to be able to handle the uncertainty in the human environments and so on. And this is actually one of the main reasons that I developed this new group here at the TU Darmstadt. It's quite new. It just started. But one of the main problems that I wanted to study, it's okay, how can we apply these amazing results that we see in deep reinforcement learning in other settings for robotics, and what are the problems that classical control and planning cannot handle. In this work that I will present, we focus on two main problems. The one is the high dimensionality of real world problems for robotics and the data collection with robotic systems. And as I said before, deep reinforcement learning methods have seen some great successes in different settings, especially in simulated environments. However, the unsafe exploration and the prohibitive amount of training data and the interactions with the environment that they require make them not possible to be used on a real robotic system directly. So some directions that could help us gather data and have safe, sample efficient algorithms, consider imitation learning, model-based learning, and off-policy learning. And in these recent works that will appear in ICRA 2021, we try to see how we can accelerate this skill learning and optimize policies, either using learning from demonstration or model-based approaches. So the first actually work considers latent movement primitives. So it's not a deep reinforcement learning setting, but rather a policy optimization approach that is based on movement primitives. And the second one, it's based on model predictive actor critic algorithm, where we consider model predictive rollouts and of policy optimization for mixing data that are gathered through the real environment, but also through model-based rollouts. So I will start first with the first approach of the latent movements optimization. So imitation learning is a very good method in order to acquire control policies when there is not an available accurate world model and when we don't have a clear task specification. Moreover, it's a very good approach for non-expert robot users, so for people that are not familiar with robots, to program robots, to transfer new skills, to teach robots new skills. And in this particular field of learning from demonstrations, movement primitives have been used and are a broad family of dynamical systems that are used to parameterize robot trajectories. And in particular, in our work, we are considering contextual reinforcement learning problems where there is some task-related context, let's call it C. And this context is, let's consider descriptions of some task-specific parameters. The context can be seen either like a description of the current state of the task, for example, the position of an object that needs to be pushed, or as a goal, for example, the desired liquid quantity that needs to be put into a ball. So let's consider QC to be a distribution over these possible contexts, and the omega will represent the parameters of the movement primitives. So since so our objective here is to find the optimal policy that maps movement and context. In particular, we need to learn this parameterized density function. And since this trajectory depend on the context and the behavior of the human demonstrator, they can be modeled as this stochastic mapping of omega given C. Here, this R function is a reward function that indicates how well a particular movement is that is parameterized by omega is performed according to a context C. So given then our objective, we should recognize that this objective is not straightforward to be optimized, as we need a way to approximate this generative model that it's depending on the movement parameters, but also on the context. And one possible way to approximate this distribution is to rely on learning from demonstrations. So let's consider, for example, N demonstrations. Then the imitation learning objective is the one that tries to maximize, to find to define the parameters, the optimal parameters that describe the joint distribution of movement and context here, P theta, that approximates the distribution of the samples omega I Ci that were collected by the demonstrator. From this particular distribution, then it's quite straightforward to actually find the conditional distribution omega over C through probabilistic conditioning. And subsequently, this is important because we aim to apply reinforcement learning for policy improvement here. And this requires the knowledge and the use of this generative model for generating trajectories over contexts, as we will see in a few slides later. But the problem is that these parameters are usually high dimensional, and this hinders the optimization problem. So instead of optimizing over the high dimensional omega, we introduce a latent representation over these parameters and the context that will allow us to perform the policy optimization robustly. So as I said, we consider in this work the probabilistic movement primitives that allows a probabilistic treatment of the movement primitives. So they consider also the variance of the demonstrations. And this provides us this distribution of the parameters and context over the demonstrated trajectories. However, we said that in our work, we do not want to work on this high dimensional parameter space, but we rather want to reduce the space and search into encoding the nonlinear dependencies between movements and contexts. And in this work, we introduce a mixture of probabilistic movements that encode in this this latent space that represents jointly the movement parameters and the motion and the context of the motions. And this model is learned through expectation maximization. So in particular, we were inspired by the mixture of probabilistic principal component analyzers. And here we will see a bit through the probabilistic model, where we have a latent variable K, that is the categorical latent variable for choosing a specific cluster. Here the pi is the categorical weight. Z is the latent variable that represents a specific movement context pair in its cluster. And the epsilons here represent some isotropic noises that are helping us to compress the noise that exists in the demonstration. So they actually play the role of the denoiser in the generative models. And the grouping of the last two equations actually give us the MPPCA model. So we get this mixture of probabilistic principal component analyzers. This model, as I said, is trained through expectation maximization. So what we achieve is to have this generative model that we want, and in order to perform policy optimization. And what we need is basically to sample a cluster given a certain context. We can then sample the latent variable over the parameters, and through this equation we can basically reconstruct the actual parameters for the robot motion. And this generative model captures these nonlinear dependencies between context and the robotic movement. And this defines a convenient latent representation, and we can maintain mathematical tractability, which allows us then to have a closed form solution for policy optimization. And in this particular policy optimization approach, we introduced several algorithmic advances, like incorporating importance sampling for leveraging all previous experience, both in from the demonstrations, but also from the new interactions with the environment, a KL-bound trust region that I will talk again later, and context regularization. So how we are going to optimize this now parametric model, since we have acquired this initialization of our generative model through demonstrations, these parameters allows us to project for its variable k and z, for its latent variable, to a specific movement context pair. Since this projection should remain fixed, we need to optimize only over the distribution of these latent parameters k and z. So these omega and c parameters remain fixed from the learning from demonstration objective. And we are currently optimizing only on the latent variables. Since these are remaining constant, we can include them into the reward function. So our objective in the end is formalized as you see here. And this formulation provides this desirable latent representation of the policy, where we see both latent parameters being considered in the policy that we need to optimize. And what we later do is that we interleave policy optimization and data gathering. And this means that in every new iteration, we consider all samples that are collected from all past policies, from all past experience. And for each new set of parameters theta, we obtain a new conditional model, p theta over the movement parameters conditioned on the context, and the new context distribution that allows us to collect new samples. And in order then to reuse this past experience, we need to do off-policy estimation. And we use self-normalized importance sampling that it's been known to have lower variance than pure importance sampling, and at the price of introducing a small bias. Hence, in each iteration, the data set is composed of samples that are generated by all previous policies, and we compute the importance ratios, here denoted as rho I, for each pair of samples zi and ki, so from each of the latent variables, by using the current policy, let's call it p theta, which is at the numerator, and the denominator contains the mixture of all the past policies over the samples that we have collected. Moreover, while during the policy optimization, the estimated likelihood over the context can diverge from the true one, from the desired Q original distribution over contexts, this can cause high variance of the estimation. In order to avoid this, we try to encourage the new distribution over context to stay close to the initial distribution of context that we learned from the demonstrations using the KL divergence. And finally, we also introduce a trust region regularization in order to obtain a robust optimization process, where we use the KL constraint between the two subsequent policies in order to avoid the premature convergence to a local optima and to guarantee this smooth optimization process. And usually this KL constraint is approximated from samples that are generated by the previous policy. And since in our case, the KL is defined between the current and the previous policy, which are dependent on the latent variables K and Z that have a closed form, we are able to compute also the KL in a closed form given a specific context. And here we can see some of the toy experiments that we have conducted in a 2D richer environment for sanity check and in order to test against the state-of-the-art method that uses dimensionality reduction, is this CT by Colomé and Torres, where they were actually doing dimensionality PCA reduction in the latent space, but due to the fact that the model could not have the probabilistic tractability, they would rely in some, let's say, heuristics in order to do later on relative policy search. We also have considered a baseline based on without any dimensionality reduction, just to do a mixture of Gaussians followed by relative policy search. And our oracle, or like our demonstrator here, is the inverse kinematics. And we can see that for different number of clusters or different possible positions in the world, the LAMPO approach performs equally well as the inverse kinematics. But we also tested it on a more challenging setting because we wanted to see whether or not it can learn the full dynamics of the environment. Then we considered different obstacles in the environment, and we used as demonstrator RRT star, which of course can solve the problem optimally. And we see here that the LAMPO gets close to 92%. And this gives kind of a trade-off between having the perfect dynamics and between being able to optimize over tasks that we will see a bit later that cannot be specified and use a planner, for example, for doing a pouring task with liquids.
And here number of iterations mean here?
It's interactions. Each iteration is an interaction with the environment that consists with, in this particular, I don't remember, in the other ones is like 50 new interactions depending on the specific tasks.
So is interaction an episode or interaction is one time step?
Here it's an episode, yes. So here it's a complete episode because it's episodic reinforcement learning.
So one iteration would be 50 episodes and sort of like...
sorry. Okay. 50 steps in each episode. Yes, you are correct. So 10 iterations was like there are 10 episodes. So yes. Here we can see some simulated task for, again, a rich target and the closed drawer, where we can see that we obtained smooth policies. And we transferred also on the robot with we trained on the robot initially, again, with a reaching task initialized with 50 demonstration, where we can see a suboptimal behavior. And then after some more interaction with the environment, we managed to have an almost perfect reaching behavior. And we have also done the pouring task. So here the objective is for the robot to learn to pour the desired amount of sugar into the bowl. And we see that from the initial demonstrations, while the robot learns to execute the pouring action, the actual, it cannot control the amount of the quantity that it pours. While after some further interactions, we can see that we are able to actually optimize the policy and more or less achieve very good behavior compared to the desired pouring quantity.
When you use the full arm, either in the reaching or the pouring, what is the action space?
Here they are the joint in the joint space. We are not considering the task space at all. So we are using kinesthetic.
It's a full sort of joint space.
Yes.
Interesting.
Yeah. The ProMP framework allows to be able to optimize over the whole joint space. However, this is one of the reasons why we need this compact reduced representation, because, for example, when you want to use a full ProMP for this kind of trajectories, you would have to consider like, how can I say, parametric space more than 50 different parameters. And in the reduced space, you can work like with 10, 15 and have a much better, you have a closed form solution for optimization, and then consequently much better performance. So we were quite happy with this result. And yeah, this actually finishes this part. So I don't know if you have some questions for the primitive section, because now I will go to the deep DeepRL, or if you want to ask questions later.
Actually, I have a question.
Yes.
So you mentioned that the noise distributions that you assume have isotropic noise.
Yes.
Or isotropic covariance. So
yes.
I'm wondering, are there cases where you would consider the heteroscedastic case where you have different levels of noise at different parts of the state space? Would that arise in practice?
This is a very good question. So first of all, the isotropic assumption is the one that is fundamental in MPPCA. So it considers the isotropic noise there. So in order to have this kind of, it depends, I think, on the demonstrator. So if still the setting of the demonstrations is very specific, and the demonstrator is providing this kinesthetic demonstrations in a particular way, I don't think you can have this kind of statistics in your noise. So you can assume that they can be quite well modeled by the isotropic noise. But yeah, I mean, one of the reasons why I wanted also to explore this different approach is also for cases when you cannot provide good demonstrations, or in cases that you cannot even be able to provide demonstrations for robotic tasks.
Thanks.
I will continue then. Okay, so I will now present you our second work, the model predictive actor critic. So as we know, reinforcement learning algorithms, and okay, we will talk about now deep reinforcement learning like soft actor critic. They sample actions from a policy, they act on the real environment, they collect some transitions, we store them into a buffer, and then we perform off-policy optimization to learn to update the policy and the Q function, our critic. However, even if SAC is the state of the art in model-free reinforcement learning, deep reinforcement learning, it needs some hundreds of thousands of interactions with the environment of samples. So this makes it, and it also incorporates the maximum entropy objective for exploration. That makes it a bit difficult to be applied into robotic systems. Some recent approaches have considered, okay, they said, since we are gathering this data, why don't we also learn the dynamics and try to do model rollouts to collect data without interacting with the real environment? And this actually gave some very good results, like the model-based policy optimization approach. What we have considered was, okay, how can we handle better this model-based rollout? So in particular in MBPO, the model-based policy optimization, they do kind of a greedy rollout. They use different samples. So we consider probabilistic ensembles that are the state of the art of Bayesian neural networks, as they are capturing very well the statistics, aleatoric and epistemic uncertainty. And they do a greedy model-based rollout in the sense that they choose different ensembles. They in every step they also consider different models, and they apply actions from the policy without caring whether or not these transitions make sense or not. However, also this noisy or not greedy selection gave very good results for them. We, on the other hand, we were inspired by the model-based approaches. In particular, the method from Lowry et al., the plan online learn offline, the Polo paper, as we say it. They have proven that when you have the perfect dynamics model, and when you can estimate quite well a value function, you can actually have a model predictive controller whose behavior can be optimal given, of course, the error in the approximation of the value function. In our case, we extended this bound to consider cases where, okay, when you don't have the perfect model, which is most of the cases. So we augmented their outcome by considering the error on the approximation of the dynamics. And this tells us that when you are learning the value function and you are also learning the dynamics, if you have a sufficiently good approximation, then your policy through the model predictive control will be as good as the optimal behavior. We wanted then to leverage this approximate MDP, so the MDP that you are learning the dynamics, to guide the samples in an information theoretic manner. So we were following the model predictive path integral approach. So in this setting, we are considering model predictive rollouts with relative entropy exploration while acting on the approximate MDP. And to give you some more theoretical insight from the MBPO approach, they have proved the model-based monotonic improvement, where they actually, what they proved was that when you are acting on the dynamics model, so in the approximate MDP, and you have a similar behavior as acting on the real MDP, given this bound that considers the approximation error on the model and the policy. So what we have considered here is actually not to do this greedy model-based rollout, but rather to do a model predictive control in an approximate MDP, more or less. What can we leverage from this? So we have let's say the exploration from the model-free approach, and in particular from SACS, we have a very good exploration strategy that can allow you to visit dynamics that you otherwise could not model. So you are having a good approximation of the dynamics. We also use the approximation of the soft value function, again, from soft actor critic, that can be used inside model predictive control to do the look ahead planning, so to have a better estimation of the quality of the trajectories. And we apply this information theoretics, so the importance sampling that exists in model predictive path integrals, in order to select locally good samples, so locally good trajectories, and use them to accelerate the policy learning. And indeed, we will see now later in the results that this gave a very big advantage. So to give like an algorithmic overview here, MOPAC, the model predictive actor critic, requires an actor critic model free algorithm like SAC. So we need to, in order to collect transitions and use them later to learn a model, where we use the ensembles as in other works. We then use the model to execute our model predictive rollouts, starting from some random initial true states. And we simulate the rollouts while also using the target value function in order to allow this look ahead planning for future states. As I told you, our method is inspired by the optimization process of the model predictive path integral in the approximate MDP in order to collect optimal trajectories and fill the model replay memory. We then continue by sampling transitions from the augmented buffer that consists of sampling some transitions from the environment and some transitions from the model in order to optimize the actor and the critic. And this combination guarantees this optimal skill learning and reduces the necessary physical interaction with the environment. And this makes it suitable for real robot training. And here we have some of our results in simulation in the OpenAI tasks of the walkers. And you can see the increasing advantage of MOPAC against the MBPO, SAC, and the model-based reinforcement learning approach. And you can see like here a bit better in the cheetah how much faster and natural the MOPAC behavior is in only 60 epochs. After these results, we were quite happy. We said, okay, let's make a robotic experiment. So in this particular work, we were collaborating with the Grab Lab from the Yale University with Andrew Morgan and Aaron Dollar. And we have used their open hand in order to construct some tasks like the valve rotation and finger gating in order to test our algorithm. And this in-hand manipulation is quite commonly used in reinforcement learning as a test bed for deep reinforcement learning methods. And we wanted to make some similar task. And the cool thing is that the open hand from Yale University, it's actually the CAD models are free and everybody can download the designs and 3D print it. They put the motors according to the design constructions and have their hand and execute the same experiments as us. And you see also the kind of the setup that we have done in the lab. And here we see the pentavalve rotation. So now the hand has to just rotate the valve so that it achieves the desired position. So the red thing should come to the front, the red mark. And here, interestingly, the hand uses only 2 fingers to solve the task. Both of them all of them converge in the end. The MOPAC is faster, and we wanted to challenge it a bit more. So we considered the round valve rotation. Here, consider that you also need to grasp the knob. So consider like a doorknob that you have to grasp it and rotate it. And this is more challenging. So this needs you to learn the dynamics, and you can see the increasing advantage of MOPAC compared to MBPO and SAC. And finally, since this hand was originally designed by the Grab Lab for doing finger gating, we wanted to do the actual finger gating, which means that you have to grasp the apple, rotate it, regrasp it, rotate it, regrasp it, rotate it, till the apple rotates till desired orientation. And of course, it does. You don't have to. You shouldn't let it fall, and it shouldn't rotate like here with the MBPO. And we can see again the much better behavior and smoother and better policy that we obtain with MOPAC. So this concludes my talk, and what we were trying to consider in these works was challenges that we have due to the high dimensionality of our real world problems, and how can we do effective data collection in robotics. What we have seen is that reduced latent representations are beneficial for learning complex skills, even when we are using movement primitives. These hybrid model-based and model-free learning algorithms provide an efficient and controllable data collection. And we believe that combining the above can lead to a sample-efficient and safe policy optimization methods. And this is an approach that we will continue working on also in the new group. So thank you very much for your attention. And if you have questions, I will be happy to discuss.
I think this was wonderfully done. I'm personally very excited about some of this work. Questions from students? If not, I will sort of start peppering. I think one question I had is, in a number of these work, particularly LOMPO style off policy or offline style work, how many demonstrations do you need to start with, and how does it scale with, let's say, complexity of the tasks? You showed examples of different kinds of tasks.
We don't need, so depends again from the different tasks. For example,
so let's say the pouring task, right? That seems like an interesting sort of real robot setup.
The pouring tasks needs 100 demonstrations in the beginning, and you see the suboptimal behavior. It learns actually the motion, but it doesn't learn the actual pouring behavior, I mean, to control how much it should pour. And then the new interactions are 225. So plus 100, you need like 325 new data in order to learn the pouring task. Yeah.
So
in this particular case, yes.
So when you start with a lot of data, just data as in not new interactions. So my understanding is you start with 100 demonstrations and 225 episodes of actually sort of like learning interactions. what is
Yes.
like the zero-shot performance when you start with whatever you can learn from the data?
It's not visible. It was in the beginning of the video.
Oh, there was a graph. So then the question.
Yeah, it starts like in 170, 070 something and goes
So
to
if you
one.
start from like nothing, right? If you don't start from demonstrations at all.
Yes, this makes sense. But the problem is that for this particular approach, you need to learn this generative model here. And in order to learn this generative model, and because you need to learn the mapping to the latent space, you cannot begin with like exploration, let's say. So this particular framework needs the demonstration in the beginning to, let's say, give you an initialization of your latent representation. So in general, Deep ProMP and the movement primitive setting require to be initialized so that they can be further improved in continuation. Yeah.
While others may have questions, I'm just too intrigued, so I will hold my questions. I see Florian has a question. Go ahead.
Sure. Yeah. So I have a couple of questions. So the first one for Lampo. If I remember correctly, you were using EM in order to
Yes.
infer some of the primitives. So I'm just wondering why not use variational inference for that for the same purpose?
It could be, yes. You can also model it as a variational inference problem. We have used expectation maximization particularly because it was convenient, because the model directly is this MPPCA model that is being optimized with expectation maximization. But yeah, I also agree with you that it would be rather interesting to solve it as a variation. And then maybe you don't need these assumptions on the noises. Of course, you will need again a prior there, but yeah, it's an interesting approach.
So the other thing that I was curious about is for the second work. For MPPO, for example, I remember that there was some not heuristic, but empirical type of selection of how much to trust your model, and then how to transition to the more predictive.
To be fair, they had in the paper a study of how the model is good or not.
Yeah.
In practice, this is never used in the paper. In the algorithm. It's a nice addition, but it was never used in the paper. The heuristic that they are actually doing, and I think this is like an advantage that they have so they can learn fast compared to SAC, is that they add a lot of noise. So we know already that actor critic needs like noise in the data. So they do tricks like they sample different ensembles. So usually in the ensembles, you have like 5 ensembles. In our case, we keep the dynamics fixed because you cannot do optimization if you are every time changing the dynamics, basically. So they are changing the dynamics at every step. They are also, if I remember correctly, do some weird exploration with the action, but I'm not sure. So they don't consider, so basically it's a hyperparameter of how long the horizon is. And this is, for example, something that we are looking into. Even in the optimization process, you can plan longer horizons, especially because you have the value function, but still there should be something that can tell you how long the horizon is. And this was like something that I wanted to understand. How can you have some kind of information on how long the horizon in the optimization should be? I mean, in general, this is a question that I have in model-based reinforcement learning, not in particular for this algorithm.
Yeah. It seems like it should be a bit state and action specific, right? So in areas of the state space where you're very confident, you should just go ahead and increase the planning horizon as much.
We actually are now trying to use some kind of intrinsic motivation. So try to consider, okay, you have a SAG, you have the maximum entropy, it explores, but why not explore where your model is not good, for example? So try to optimize better in order to plan better. So this is something interesting, but the problem is that usually the way that this is being evaluated in literature is not so statistically correct, given how you collect the data. So theoretically, you should have an optimal policy that will give you expert data, and then always try to. It's not straightforward, and we are like also trying to look into this.
Great, thanks.
Any further questions from anybody else? So I have now broader questions about this is not like particularly for LAMPORM or PAC, but maybe your experience with working with these sort of algorithms. At this point, you have experience doing this. If you were to practically do this, what would be a takeaway for like a new student? It's like, and this can be, we can stop recording at this point if you need us to, so that it can be genuinely an honest answer. But the thing that I would love to understand is, and I know, for example, I've known Jan's students who worked on ProMP, so Gerhard and all the others before them, and who have graduated and moved on at this point. But what I want to understand is, if I need to do a contact-rich task, or even like pouring, where it's not necessarily contact rich, but it's let's say dynamic, and the dynamics is fairly nonlinear, right? What is a practical way to build a robot skill that is reasonably robust?
Yes. I like your question. You don't need to stop the recording. I'm fine with expressing my my thoughts. So yeah, movement primitives are quite a flexible tool, right? They will never give you the optimal policy most of the times. They will not generalize to all possible questions. Here, with this context, the probabilistic approach, we were able to make them generalize in some specific situations. In my opinion, they are not the optimal tool to use for all specific problems. For sure, we need a kind of a skill library. What I am considering actually is a fair decomposition. So I am clearly going back to consider approaches like switching dynamical system, where you can encode a complex task with probably local linear controllers and try to combine those effectively to achieve a more complex task. So this is basically one of the approaches that I want to work on. So not necessarily making our life difficult by trying to encode a very nonlinear complex trajectories into a simple policy, but rather decomposing it and composing it according to the needs. But in general, having the ProMP or whatever MP as a skill library, it's a good approach. Again, you need to have a high-level controller, a meta controller, whatever you want to call it, that will tell you when to use what. You cannot encode all possible tasks, in my opinion. So it's better that you have a skill library, some primitive, really primitive, in my opinion, locally linear controllers, and try to combine and optimize over them if possible.
Okay.